Hello. Good evening, all.
Good evening, sir.
Am I audible? Yeah. Okay. Yeah. So, so last class we were seeing about graph, right? We started with graph. So, do you have any doubts in respect to graph? Okay. So first we saw what is a graph, and then how to represent a graph using the matrix format as well as the list format, right? So if you see in a matrix format, it is just entries. So you have the edges, you have the sorry, vertices and the edges. Okay, so these numbers represented here are vertices, and the values which are present over here are edges, edge weights. Okay, and you can see wherever there is -1, it means there is no connection, and wherever there are values, it means it is a weight of that particular edge which are connecting these two nodes. Yeah, and then so we saw what is a connectivity matrix. Connectivity matrix is nothing but it just says whether two nodes are connected or not. 0 represents not connected, 1 represents connected. Okay, and then we saw how to implement using linked list. Okay, so in a linked list format, you'll be having a set of heads. Okay, so number of vertices is equal to number of heads. So there'll be vertex number of heads, and then each head will be pointing to a linked list. And in that linked list, you'll be having this particular node. Okay, if it is a zeroth linked list, zeroth node connected to which node and what is the weight. So like that, you have a list. So the first number represents to which node it is connected and the weight of that particular edge connecting these two nodes. Okay, like that, if you fill, you get the entire list of a list of linked list would be there. That would represent a graph. And we also saw which is better, when to like have a linked list and when to have a matrix format. Okay, if it is a sparse graph, then it is better to have a linked list format. If it is a like a complete graph or a near complete graph, it is better to have a matrix format. Okay, now let us see how to traverse. Okay, so we saw tree traversal, right? In tree traversal we had in order, pre-order, post order. Like that, we have in graph traversal we have DFS and BFS, depth first traversal and then breadth first traversal. So we'll take a graph. I'm searching for a branch. Yeah. Okay. Yeah, this should be better. So let us take this graph. Okay. So now, like, so shall we work out something? So if you have a paper and pen, just take it out, and then I want you to create a list. Okay. I want you people to construct a list format of this graph representation. This graph want you to represent as a list format. So like you have how many vertices are there? There are totally 9 vertices. Okay, so as of now, don't worry about the link. So just write 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and this is an unweighted graph. So now here you're going to write whatever nodes are connected to 1. That's it. Okay, so what are nodes are connected to 1, 3, and 4. And it is better if you write it in ascending order. Okay, so 3 and then 4. Like that. The second node, 2. What are the nodes that are connected to 2? 3, 5, and 9. Like that, you also take a notebook and then just make a note of this. And then to 3, 1, 2, 4, and 9. And for 4, 1, 3, 5, 7, 9. Okay. Then for 5, 2, 4, 7, 9. And for 6, 8. For 7, 4, 5, 8. And for 8, 6, and 7. For 9, it is 2, 3, 4, 5. So you can consider each and every value which I have written as a node in a linked list. Okay. So you can consider, just imagine this, it like a linked list format. Okay. So now what we're going to do is we're going to do a traversal. So as I told you, like in a graph, okay, so you don't need to follow a hierarchy. Okay, there is nothing called a root node, then the next level to root, not like that, right? So whereas in a tree, you'll always start the traversal from the root, right? So here you can always choose your own start point. Okay, it can be either 1, it can be either 9, it can be either 4, 5, whatever. Okay, so let us start with what number? Let us shall we start with 3? Okay, we'll start with 3. Okay, so there are two types of algorithms, traversal algorithms. One is depth first traversal. So depth first traversal. So as the name suggests, you're going to go depth-wise. So depth-wise in the sense, like you're starting from 3, right? So which is the first neighbor? So you have to see with two things. Okay, so one is the next node which you're going to take should be a neighbor, as well as it should be unvisited. Okay. So for 3, the first neighbor is 1. Okay, so forget about all other neighbors. You're just going to take a single. Okay. So now come to 3. Sorry, come to 1. So from 1, which is the first neighbor to 1? Yes.
3.
Which is the first neighbor to 1?
3.
Hello.
Hello.
I'm not able to hear. Yeah. So 3 is the first neighbor, right? But we can see that I started from 3 only. So it is already visited, right? So even though 3 is the first neighbor, we can go and search for the second neighbor of 1. Okay, so 1 is having a second neighbor as well. If it is not having a second neighbor, you will go back to 3 and find for alternate path. Whereas 1 is having a second neighbor. So you can go for 4. Okay, so now come to 4. So let us keep track of that. So first 3, then 1, then 4. So for 4, which is the first neighbor? It is 1. It is already visited. 3 is also already visited. Okay, now the next neighbor is 5. So how will you keep track of which neighbor it is? Which neighbor to search? So you just have it here. Okay, so for 4, so first you take 1. So 1 is visited. 3 is also visited. Next is 5. 5 is not visited. So the next neighbor I should take is 5. Right? I'll go to 5. Are you able to follow? So from 5, if you see, we have 2. Okay, 2, which is the first node, right? First neighbor. So 2 is not yet visited. So what we will do? We will go to 2. Right? Now we are at 2. So from 2, if you see, we have 3, the first neighbor, 5 is the second neighbor, and then 9 is the third neighbor. So 3 and 5 are visited. So 9 is not yet visited. So 9. Now we are at 9. So if we see from 9, 2 is visited, 3 is visited, 4 is visited, 5 is visited. Yeah, it has to be descending order, ascending order. Yeah. I didn't get your question. So it will obviously be in ascending order only. Why? Because see, how will you construct a list? You'll construct a list from the matrix only, right? In the matrix, you have the values in ascending order only. So you'll go and search for the second node, what are nodes are connected to it. You'll have first 1 is connected, then 3 is connected. Okay, so it's obviously comes in ascending order only. So you no need to worry about that. Okay. So now where did we stop? Yeah. So 9. So we are at 9, right? So with respect to 9, all 4 nodes are visited, right? So 2, 3, 4, 5 are visited. Now what will we do? We have to go back from where 9 came from. So from where did 9 come from? From which node? From which node 9 came from? Two. Yeah. So I think I'm not able to hear your voice. Is it so? Someone unmute and speak. No, I'm not able to hear. Check. Is it okay now?
Hello.
Yeah, now I can hear. Is it okay for you?
Yes, sir.
Okay. Yeah. So now, so 9 came from 2, right? So I have to go back to 2. So are there any other unvisited nodes with respect to 2? 3 is visited, 5 is visited, 9 is also visited, right? So with respect to 2, still there are no more nodes which are unvisited. If there are any unvisited nodes, then I have to take that path. But since there are no other nodes which are unvisited, so I have to go back to from where it was called from. So where was 2 called from?
5.
5. Yeah. So now go back to 5. So are there any unvisited nodes with respect to 5?
7.
Yes. Okay, 2, 4, 9 is 2, 4, then 7. So 7 is not visited. So come to 7. So from 7, 4, 5 visited, come to 8. Right? Okay. So from 8,
6.
yeah. So still it is not over. Okay. So now what you have to do? We have to return back to the main function itself from where it was called. So since as per we have seen it is over, but it is not yet over. You have to complete the algorithm by tracing back to from where it started. Okay, you have to go back to 3 itself. So from where 6 was called? 6 was called from
8.
8. Yeah. So 8 was called from. So no other nodes for 8, right? Unvisited nodes. So go back to
7.
7. So 7 was called from which node?
5.
Yeah, 5. So any unvisited nodes? No unvisited nodes. So go back to which node?
4.
Yeah. From 4 to
1, 1 to 3.
1 and then 1 to 3. And still there are no more nodes, right? So go back to the main program from where it was called from. That's it. So this is how your DFT works. Depth first traversal works. Okay. Now let us see the proper tracing. Okay. So for DFT, we're going to make use of stack. Okay. So we're going to make use of a stack data structure to implement this DFT algorithm. So now let us not go to the graph itself. So with this graph representation, we'll make use of a stack, and then we need to make use of one more list which will keep track of the visited. Okay, whichever nodes are visited, that should be kept track of, right? For that we have one more list. Okay, so I'll just mark it from 1 because here also nodes are starting from 1, right? So while implementing, the list index starts from 0. Okay, keep that in mind. So since the node numbers are starting from 1, I am putting 1 here. So initially none of the nodes are visited, right? So if they are visited, I will mark it as 1. If they are not visited, it will be 0. Okay. So I have to initialize this entire list with zeros. which means none of the nodes are visited. Now I'll take a stack. Okay. So stack index, I will mark it from 0 because it's a separate list, right? And then I will mark top. Okay, so top keeps on changing. As of now, it is pointing to -1. Okay, it is pointing to -1. Okay, fine. So the procedure is, so we have the start node. We started from which node? 3, right? So the start node is 3. Okay. So now what you do is only for the first step. Okay. So only for the first step, what you do is take the start node, start value. Okay. Mark it visited. Push it to the stack, and then you print it. So to keep track of whatever nodes are in which order we are traversing. Okay. 3 operations you have to do. One is marking visited. Next is pushing to the stack, and third is printing to keep track of in which order we are traversing. Okay, so first step alone you'll take from the start. From the second step, what you have to do is, so now what happens if you push one element to the stack? What happens to the top? Top will point to 0th location, right? 0th index. Okay. Now on, what you have to do is take the topmost element. Taking means you're not popping it out, just considering. Okay, remember that this in mind. You're not removing it, the top element from the stack. You're just considering the top element. So the top element is 3. So now what you do is come to this graph list. So from here, what you should do is you should start traversing in this linked list. Why you're traversing is you're going to find the first unvisited node. Got it? So you're going to traverse this list to find out the first unvisited node. So you will break the loop. You will have to put a loop, okay, to find the first unvisited node. You're going to put a loop. The first node is 1. So what you do, you will check whether it is visited or not from this array. So this is the visited list. I'll just mark it as V. Okay, so here you'll check whether 1 is visited or not. So 1 is not visited. So if it is not visited, what will you do? 3 steps. What are the 3 steps? First you will mark it visited, then push it to the stack. Okay, and then print it. Done? Any doubts? Okay, so let us proceed. Now what you will do is you will consider the topmost element. So the top element is 1. So if it is 1, simply go to the first list. Okay, so you'll check whether the first element of this list is visited or not. Yes, it is already visited. Now go to the second element. Second element is 4. 4 is not visited, right? So what will you do? What are the 3 steps?
Change it to 1, then push it onto the stack and print
Yeah.
it.
Mark it visited, push it to the stack,
Change top, increment it.
and then
Print the
print it. Okay, so now the top element is 4. So come to the fourth list. Okay, so now we have 1 already visited, 3 also visited, 5. 5 is not visited, so mark it visited, push it to the stack, and then print it. Okay, now the topmost element is 5. So 5 is, okay, fifth list is this one. Okay, so 2 not visited. So mark it visited, push it to the stack, print it. Now the topmost limit is 2, the second list, 3 visited, 5 visited, 9 is not visited, mark it visited, push it, 9. Okay, now the topmost limit is 9. So 2 visited, 3 visited, 4 visited, 5 is also visited, right? So since all the elements are visited, what you have to do is, so now no need to keep this in the stack, right? Because all the nodes, all the neighbors are processed. So simply pop that element out of the stack. Now the topmost limit is 2. So again, what you have to do? Check for the first unvisited node. So 3 is visited, 5 is visited, 9 is also visited. So remove that element also from the stack. Now the top element is 5. So 5 is, sorry, in 5, 2 visited, 4 visited, 7 not visited. Okay, so mark it, visited, push it to the stack, and then print it. Now the topmost element is 7. So for 7, 4 visited, 5 visited, 8 is not visited. So mark it visited, push it to the stack, print it. Now topmost element is 8. So for 8, 6. 6 is not visited, mark it visited, push it to the stack, print it. Sorry, this is 1. Okay. And now the next what you have to do, the topmost number is 6, right? See, you can see that all the nodes are visited, but still we have to proceed. Okay, till what? Till the stack becomes empty. Okay. So the topmost number is 6. We have 8 already visited, so pop. No more elements are there, so pop. Okay, I'll just remove the top because fine. Next is 8, 6 visited, 7 also visited, so pop. 7, 4, 5, 8 all are visited, pop. 5, 3, 4, 7, 9 visited, pop. 4, 1, 3, 5, 7, 9 visited, pop. 1, 3, 4 visited, pop. And then for 3, 1, 2, 4, 9 visited, so pop. Now the stack is empty, so the DFS algorithm is done. DFT algorithm. Okay, actually we can call it in both way, depth first search or depth first traversal. Okay, both mean the same. That's why I'm telling this DFS, actually DFT. So this is the output, right? Okay, so if you see, it will be the same. Understood? Any doubts on this? Any doubts? Okay, fine. Now the question is, suppose you have subgraphs. Okay, So if you take this is a single graph only. It is containing multiple subgraphs. Okay, it is a composition of 3 graphs. Okay, understood? So in this case, suppose if we apply DFT, depth first traversal, starting from any of these nodes, okay, let's say we are starting from this node. So now what happens is only the nodes which are present in this subgraph will be visited, right? Are you able to understand? So there's no connection between this subgraph and this subgraph, right? Totally disconnected. Okay. So now what happens is if you start from any node from this subgraph, okay, you will get only the output for this subgraph. This will not be included. Now what you have to do is, like anyway, these nodes are still unlisted, right? Okay. So you'll be maintaining a list of visited and unlisted nodes. Okay. So how many ever nodes are there? Those many values will be here. One second. So suppose that in the previous graph itself there was a subgraph. Okay. So like this. So suppose the previous graph for this graph and this was the other graph. Okay. Subgraph. Now what happens is all these nodes till 9 will get visited, whereas the other nodes will be still unvisited. Now we can make out, right? So what are the nodes which are unlisted? Now what you do is you just iterate over this entire visited array and then find whether there are any unlisted node. Okay. So you can see the first unlisted node which is coming is node number 10. Now what you do is just call the DFS algorithm once again using the start value as 10. That's it. Okay. Did you understand? So you'll just iterate over this entire listed list and then check for the first unlisted node and then pass the start value as whatever is the first unlisted node. Here 10, right? You pass 10 as the starting node and whatever nodes are connected to 10, that will be coming as visited. Okay, there might be some more unlisted nodes also. Okay, suppose 10, 11, 12, 13, 14 are all is a subgraph. Again, few elements would be unlisted coming as part of the third subgraph. Okay, so what you do? Again, do an iteration till the end and then find the unlisted node and then pass that for the DFT. Okay, fine. Did you get this? Any doubts? Are you able to understand the last part? If there are subgraphs, what you should do? Okay, I repeat. Okay, so if I apply DFT starting from this point, okay, now what happens? First it comes here, then is the second node, and third node. So no other neighbors. So go back. So it'll come here, fourth, and then it'll go there, return back, come here, here, return back, here, return back, return back, return back, return back. Right? So this is what would happen in this if we apply DFT starting from here, right? So it is not connected to this graph at all, neither this graph. So now what happens? These nodes will still remain unvisited even after applying DFT for starting from this location. These two nodes, okay, these two subgraphs will be, all the nodes of these two subgraphs will be unvisited. So how to keep track of whatever nodes are unvisited is making use of this visited array. Okay, so what will happen once it comes out of the first DFT algorithm? All the points in this subgraph would be marked as visited. Okay, and all the points in these two subgraphs will be marked as unvisited, will be still 0. Okay, now what you do is just iterate this entire list starting from 1. Okay, check whether any unvisited nodes are there. So you can see that all these nodes are visited and 10 was unvisited, right? So 10 is unvisited. Now what you do is you put the DFT algorithm, that is you call the DFT algorithm starting from 10, making the start node as 10. So now what happens? Again, it starts from here, and then it calls okay, it does the DFT traversal, and then these nodes will be visited. These 6 nodes will be visited, and these 6 more nodes are still unvisited, right? So now what happens? Whatever nodes are connected to this particular node will be visited. Okay, so nodes which are connected to this node are still not visited, right? So again, you will continue the iteration, and then you'll come over here and see that it's still not visited. So call the DFT algorithm starting from 14 to make all these nodes visited. Now understood? Any doubts? Okay, fine. So now, like, so if you are doing the normal iteration method, so what happens is you have to maintain a stack, okay, and then you have to do the push operation, pop operation, all those things you have to do. Instead, okay, so you have the function. So what does function do? Function uses the stack model, right? So function works the stack model, right? So we saw in recursion also. So what we can do is we can make use of recursion in place of using the stack explicitly. Okay, because the recursion implicitly uses the stack. Okay, so I'll just help you out in doing the code for DFT. I'll just write the pseudocode. Okay, can try to build that up. So first DFT. So what you will pass to DFT is the graph. Okay, so this G is nothing but this entire thing. Okay, along with that you will pass the start node. So from where to start, and then you will pass the visited array. Okay, and as well as you need to pass the I think number of vertices needed or not. Okay, let us see whether v is needed or not. No. So we are going to make use of recursion to solve this, right? So what should be the stopping point? Okay, fine. So let us come to the stopping point later. So this is not going to return any value. So we need not bother about the stopping point. Okay. So now, uh, so this is the start value. So now what you have to do for start value, we need to mark 3 steps. Okay. You remember the 3 steps, whatever I told you. First, you have to mark it visited, push it to the stack, and then like you have to print it, right? Mm, So how to mark it visited? So v of s is equal to 1, and then simply print it. And after that, I simply do a put a loop and then do a recursive call. Why? Because I'm not going to use a stack over here, right? I'm going to use recursive function to maintain this stack. So while so now what I should do is I should iterate over this entire list. Okay, so suppose the start point is 3, so I iterate over this entire um, linked list 3. Okay, and what I would do is I would check for the unvisited node. So for iterating, I need a temporary variable, right? T is equal to. So how to take this the head of this linked list? So how to take the head of the linked list? This is actually the head only, right? Okay, so it is nothing but g of s. So in the graph, at the s position, we have the head of the linked list. Right? I take it in a temporary variable. Why I am taking it a temporary variable? I need to iterate, right? Okay. So while t not equal to none. So this is how you will iterate over a linked list, right? So what you would do? So I'll till t becomes none. Okay, I will do the iteration. So now whenever I find an unvisited node, I simply do a recursive call. So how to find whether it is visited or not, the current node? So first of all, I need to take the current value, right? So I need to take 1. So in this node, okay, I have to take 1. So how to take 1? It is nothing but t dot data. So I'll just put it in D. Okay, so D is equal to t dot data. So now I have to check whether D is visited or not. So how to do that? Just put if v of not D is equal to 0. 0 means not visited yet, right? So do a DFT call. DFT of G comma. Now which is the start node? T is a start node. Okay, so D is a start node. D comma. I think no need of this number of vertices. I can just remove that. So I thought number of vertices is needed, but actually it's not needed. And then you have listed array is the same, capital V. That's all. Okay. Now what you do is you just make a note of this, and then you take a sheet of paper, and then you need to trace a code. Okay, so just take this entire thing, and then you take some other value as the start node. Okay, take 2 as a start node. Okay, so this is your assignment. What you do is you take a paper, you can send me a WhatsApp image. Okay, so once you are done the tracing, you can send me a WhatsApp image. What you have to do is just trace this entire code. So how will you trace this? Like so I'll just show you how to trace. Initially for 2-3 iterations I will show you. So first what happens, you call DFT of. So this graph and visited are not going to change. Okay, so it's going to be the same. So this visited, you just maintain one more array here. Okay, so so S is only going to change every time. So I'll just pass 2, DFS of 2. Okay, so I'll just mark visited of yes, that is S is here too, right? So I'll mark it as 1. Okay, so you just maintain a list in the right hand side. You just mark the second position as 1 and then you print it somewhere, and then t is equal to g of s. So t is nothing but this particular value, right? So you can just mark, take it as 2x. T is equal to 2x. Or you can make it as 3x. Okay, so I need some address here. Okay, whatever address you want, you can give. And then what you do is while t not equal to none. Okay, so 2x of data is what? It is 3, right? So d is equal to t dot data, which is nothing but 3. You can directly like d equal to 3. No need to write t dot data. Okay. And then you're checking whether is listed or not. So it is not listed. So if you just write true, we call DFT of 3, right? So now we had DFT of 3. Now what you will do? So it should be like a kind of like branching. Okay, you take a big sheet of paper. Okay. So now what happens? So shall I make it in Excel sheet? So fine. So what will be the final output is first DFT of 2 is called, right? So from 2, DFT of 3 will be called. Okay. So from 3, DFT of 1 will be called. Okay. So from 1, again 3 is already listed. So DFT of 4 will be called. So from 4, okay, 1, 3, 5. So 5 will be called. So like that it goes on. Fine. So from 5, 2, 4, 7 will be called. So like that you have to do the entire tracing. Okay. So after once it reaches none, what happens? It returns back to the previous call. So you have to check till which point it is over with respect to this 5. Okay. And then you have to make a branching. Next branch will come. Okay. So from this point, if there is another branching, you'll get a right one more branch over here. Are you able to follow? So did you understand this? Any doubts in this? And the recursive logic. That's all. This is your program. Only thing is you have to understand how recursion is working. Okay, so if you have G in your hand and then the listed array in your hand, that's it. This is your logic. Only some 8 lines. This will take care of the entire traversal part. Okay, so from where this DFT should be called is, it should be called from one more function. Why we are making one more function is DFT util something like that. So first you will call DFT of G comma S comma T, sorry, V. So once, so this is the first time, okay? So now what happens after because after this DFT call is only the nodes which are connected to that particular vertex S will be visited. If there are any island nodes or subgraphs, okay, that will not be visited. So for that, what you have to do? So for um, I in range of length of visited, if V of I not or if it is equal to 0. So if it is equal to 0, what does it mean? It means it is not visited, right? So again call the DFT algorithm. This time starting with I, comma V. Understood? Now this time DFT will be called with starting point as 1, and then again it has to return back here only. Then the loop proceeds, right? Okay, so it will find for any other unlisted node, and then again DFT will be called. So repeatedly DFT will be called till all the nodes are visited. That's it. Yes, understood. Any doubts? Are you able to follow? Hello. Okay. So now let us see the next algorithm, DFT. So in DFT we use stack, right? So in BFT we'll be using queue. This breadth. So we'll be making use of queue data structure. So here, as the name suggests, what we'll be doing is we'll go breadthwise. Yeah. So now again, let us start from 3 itself. Now, so what happens in breadth first traversal is once you take a node, you will visit all its neighbors. You will not leave any neighbors at all. So visit all the one more important point is unvisited neighbors. Okay. So now what happens is yeah. So first you are starting from 3, right? So what are the neighbors of 3? 1, 2, 4, and 9. So all the 4 neighbors are unvisited. So what you do is you start doing the process. So first 1 are not visited. So mark it visited, and here also you'll do the three operations. Here you'll make use of the queue. Okay. So we'll see with respect to queue also. Now let us we'll see generally, and then we'll see with respect to queue. So all the 4 nodes has to be processed, right? Next is 2, then 4, and then 9. Next, which node you will take is 1, which is the first neighbor of 3. So here what happens is you'll go level by level. So BFT is also called as level order traversal. Okay. So level order traversal, BFT, both are same. So here, next node which you will take for processing is 1. So if you see from 1, there are 2 neighbors. Okay. So the first neighbor is 3, second neighbor is 4. And both the neighbors are already visited, already processed. Okay, so nothing will happen with respect to 1. So the next neighbor for 3 is 2. So from 2, if you see, there are 3 neighbors, 3, 9 and 5. So among these 3 and 9 are already visited, are already processed. We will go for 5. Okay, so the next node to be processed is 4. So from 4 we have 1, 3, 9, 5, 7. Okay, sorry, in order means like 1, 3, 5, 7, 9. So in this 1, 3, 5 processed, 7 is not processed. So I'll process 7. And then the next node is 9. 9 is already processed. Okay, so after 4, the next node is 9. So with respect to 9, we have 2, 3, 4, 5. All the 4 nodes are already processed. So nothing will happen with respect to 9. Next node is 5. So with respect to 5 also, 2, 4, 7, 9. All the nodes are processed. So nothing would happen with respect to 5. And then 7. So we have 4, 5, 8. 4 and 5 already processed. So 8 is not processed. So 8. And the next node to be processed is also 8. So we have 6 which is not processed. Other neighbor is 7 which is already processed. So the next node which will be processing is 6. So with respect to 6, only one neighbor 8, it is already processed. That's it. No more nodes to be processed. So the algorithm is done. Any doubts? The general form?
No, sir.
Okay. Now let us do the same thing with making use of a queue. So there are not much nodes. Okay, only till 9 it is present. Just so here we need a queue, right? So where should I put the queue? Let me put the queue over here. Here our start node is 3, right? So enqueue. So here you are enqueuing. Okay, enqueue to the queue. Okay, mark it visited and then print it. Right. So next step, what you do is only for the first step. Okay, you'll do this enqueuing, marking it visited, and then printing. From the second step, what you have to do is you have to dequeue it from the queue. Why are we dequeuing? Any reasons for dequeuing from the queue? Anyone? In the stack, we maintain till the last, right? Whereas in queue, we need to dequeue. Any reason?
Because I think queue follows the first in, first out one.
Yeah.
So if it is going first, it should be out first.
No. See, in the stack, we maintain till the last. Whereas in the queue, we are dequeuing and then processing. Okay, I'll tell you because the reason is once you consider an element, you'll be processing all its neighbors, right? So if you take 3, all the neighbors are being processed at a single time. Okay, whereas in a DFT, you just take one path. That's a possibility that still unlisted neighbors are present with respect to 3. Only if there is a confirmation that all the nodes are visited, we'll be dequeuing. We'll be popping the element from the stack. right? Whereas here, if you take a particular node, all its neighbor are definitely going to be processed. There are not going to be any unlisted nodes, unlisted neighbors for a particular node. That is the reason we dequeue and then do the processing. Understood? Yes. See, in while DFT also, when we reach the last node, that is when we know that all the nodes are visited, all the neighbors are visited, we pop out from the stack, right? Whereas here, we definitely know that we are going to process all the neighbors. So we will dequeue and then do the process. That's it. Okay. So after dequeue, I'll have a variable d, which will store the dequeued variables. 3 is there. So I dequeue, so no elements will be there in the queue. Now the element is 3, so go to the third index and then take all the neighbors. Anyway, you'll be processing it one by one only, but all the neighbors will be processed. So first one is not visited, so mark it visited, enqueue it to the queue, and then print it. Okay, second element is 2, not visited, so mark it visited, enqueue it to the queue, and then print it. Third element is 4, not visited, mark it visited, enqueue it to the queue, print it. Fourth element is 9, not visited, mark it visited, enqueue it to the queue, print it. Okay, now with respect to 3, all its neighbors are visited, all its neighbors are processed, right? Now understood why you are dequeuing it from the queue? No more unlisted nodes are there. So again do the same process. Dequeue the element from the queue. Now what happens? Which will come out of the stack? 1 or 9?
1.
Yeah. So dequeue, so 1 will come out of the queue. Okay, now the dequeued element is 1. Now go to the first list. Okay, in the first list, the first element is 3, already visited, so nothing happens. And then 4 is also already visited, so nothing happens. Okay, so 1 has been taken out of the queue. So with respect to 1, processing is done. Next, dequeue another element. 2 will come out of the queue. We have 2 in D. So come to the second list. We have 3 already processed. Okay. And then 5 is not yet processed. So mark it visited, enqueue it to the queue, print it. Okay. Still it is not done. 9 is there. 9 is already visited. So that's it with respect to 2. Now again do a dequeue operation. Remove 4. Go to the fourth list. We have 1 visited, 3 visited, 5 visited, 7 is not visited. Okay, so mark it visited, enqueue it to the queue, and then print it. Okay, next is 9, right? With respect to 4 till 7 we processed. Then the remaining value is 9. 9 is already processed, so that's it. Okay, so next dequeue 9. So come to the ninth list, last list. So 2, 3, 4, 5, all are visited, right? So nothing will happen with respect to 9. Then do the dequeue process. Dequeue of 5. So fifth list, 2 visited, 4 visited, 7 visited, 9 is also visited. So in with respect to 5, nothing will happen. Dequeue. One more element, 7. So come to the seventh list. We have 4 visited, 5 visited, 8 is not visited. So do the process. Mark it visited, enqueue it to the queue, and then print it. Okay. Now with respect to 7, all nodes are done, right? So dequeue. So with respect to 8, come to the 8th list. node 6 not visited, so mark it visited, enqueue it, print it. Okay, then 7 is already visited, so that's it with respect to 8. Now do a dequeue. 6, only element connected to a 6 is 8, this is also already visited, so nothing happens with respect to 8, and no more elements are there in the queue, that is the queue is empty. So now we can stop the BFT algorithm. Understood? Any doubts in this? Do you understand? Okay. Yeah. So like again here you have to make use of a queue for implementation. You can use this one nq dq, all these functions you can write. You know how what is nq, what is dq, all those things, right? So just follow these steps. Okay. So just you have to iterate over the entire list and then do this process whenever there's an unlisted node. Okay. Fine. So now let us go to today's topic. Hashing. So hashing, like so hashing is nothing but like I gave a gist about hashing while taking set. Okay, I hope you remember that. Okay. So for hashing, like it is nothing but you have a table. So in that table, you will search for a particular index where to insert the data. Table in the sense it's not, it's like a normal list only. So it's not nothing much. It is just a list. Inside that list, you're going to store the particular value by calculating the index where to store. That's it. Okay. So I'll explain it in much detail. So what all things you need to understand here is the first one is the hash table, which is nothing but a list. Okay. And most importantly, we have the hash size or hash table size. Okay, so this is the most important thing to determine where the elements are going to be stored. Okay, so it is just an integer. Let us say s is the variable, and then okay, so this hash function is going to determine at which index the particular data is going to be inserted. Okay, function to determine the index of the data. Okay, so and then we have some more terms, collision. So collision means what? If two data are fighting for a single index, okay, then it is called collision. Understood? Okay, so already one data is there. If one more data is trying to sit in the same place, that is called collision. And then rehashing. So rehashing means suppose the hash table is going to be filled. Okay, so suppose the hash table size is 7 and you have entered at least 5 to 6 elements. Okay, so it's almost full, right? So in that case, what you will do is you will increase the size of the hash table. Okay, I'll tell you how this rehashing is done. Okay, fine. So now let us take a few set of data and then we will do these three operations and then we'll come to collision and rehashing. Okay. So like first challenging thing is choosing the hash table size. So choosing yes. So how to choose yes is that, okay, it is better to choose yes as a prime number. So why we are choosing a prime number is, okay, for random data, okay, so if we choose a prime number, then the collision will be reduced. So it is also by research only. It is not compulsory that the collision is going to be 100% reduced. It is not like that. Okay. So suppose the data which you're going to enter is 10, 20, 30, 40, 50, 60, and then 70. Okay. So suppose if you have the hash table size as 10, what happens? Okay, I before that I should tell what's the hash function, right? So hash function is nothing but it is going to determine at which position the particular data is going to be, at which index the particular data is going to be inserted, right? So hash function is mostly it is modulo yes. Okay, so modulo yes means data modulo yes. So for every data, these are the data, right? 10, 20, 30, 40, 50, 60 are the data. For every data, you're going to apply this function and whatever is coming as the output, that is going to be the index. Understood? See what is, suppose the hash table size is 10. So what is 10 mod s? 10 mod 10? 0, right? So what happens? 10 will go and sit in 0th index. Now the next element which is coming in is 20. So 20 mod 10 is also 0. Now there occurs a collision, right? 20 also tries to sit in the same location. And then 30 also same location, 40 also same location. You get all the elements, if you take model of 10, you will get 0 as the index. Understood? So if you take 10, then that is a problem. If this data is like this. Okay, even if you take 5, again the same thing happens. If you take 4, many elements will bombard, right? Collision happens a lot of times. 3 elements collision and again another 3 elements will get collided. So like that. So if you take some numbers like this, non-prime numbers, collision will be more. Okay, if you take a prime number also, this is also challenging, but still collision is reduced. If I take 7 and if I get the elements like this, 7, 14, 21, 35, 28. So if the data is like this, what happens? Every time here also collision occurs. Are you able to get it? 7 mod 7 is again 0. 14 mod 7 is also 0. 21 mod 7 is also 0. Okay, so this is but a rare case. But this is not a rare case. Data 10, 20, 30, 40 is not a rare case, right? Most of the time, data will be stored like this only.
So,
Yeah.
so in this where you've written function to determine the index, D is all these values 10, 20.
One by one. Yeah, one by one. Not all at a time. One by one at a time. 10 mod yes.
These are the data that means.
Yeah. Data which are going to store inside the hash table.
And S is the table size.
Yes.
Okay, thank you.
Yeah. So now, yeah. So mostly the hash table size should be prime number. That's what I wanted to say. Not mostly, always. Always the hash table size should be a prime number. Now let us take this data and then let us try to insert inside the hash table of size 7 and see how it is done. Okay. Just for understanding, let us do this. Then we'll go for the collision avoidance techniques. Okay. So my hash table size is 7. Okay. So it is a list. So index starts from 0. So values from 0 to 6. Now, so how will you know that the element is already present or not? I'll just mark it as none. Understood? If it is a non-none value, then it means that some element is present. Okay. Now the data which you're going to insert is 10, 20, 30, 40, 50, 60, 70, right? Okay. So the first data is 10. And we know it is the function which you're going to use modulo 7. Okay. So hash table size is 7, right? So modulo 7. So what is 10 modulo 7? Yes. What is 10 modulo 7? 3.
3.
Yeah. So 10 will be going to the index 3. Right? So second element is 20. So what is 20 modulo 7? Yes.
6.
Yeah. So 20 would go to the position 6, index 6. 30,
2.
yeah. So 30 would come to index number 2. 40,
5.
yeah. So 40 would come to index 5. Sorry. 50,
1.
yeah. 60,
4.
4. 70,
0.
yeah. That's it. So fortunately for this data, there is no collision, right? All the elements had a unique like index. If you put modulo, so everything like sat in its corresponding location.
Sir, if there is collision, then what we do?
Yeah, I'll tell you. Next is collision. Okay.
Okay.
Now, so here there is no collision. So next we will see what happens if there is any collision. Okay. So for collision avoidance, there are two steps. Okay, so let us discuss the methods and then we'll try to differentiate. Okay, how we can classify it. Okay, how based on how the collision avoidance is happening, we can classify. So one is linear probing. Second is quadratic bobbing. And then the third is separate chaining. We'll discuss one by one. Okay. The first method is linear probing. Probing means you are checking for next locations. Okay. So linearly we are checking for next locations. That is called linear probing. Now let us take the data randomly. Okay. 12, 4, 10, 85. Okay. No, first 12. So what happens if we insert 12? What is 10? 12 mod 7?
5.
Yeah. Five. So 5 is free, so 12 will come and sit at fifth location. And 4, what is 4 mod 7? 4 only, right?
4.
So it will come to fourth location. Next is 10. 10 will come to third location, right?
Mm.
What about 80?
3.
Yeah, 80 again 3, right? So, but already we can see that 10 is present. So now what happens is in linear problem is that you will go and check for the next location whether it is free or not. Next index. Okay, next index is also not free. Now what you will do? You will go to the next index. That is also not free. So next index it is free. So you will insert 80 over here. That's it. This is linear problem. Okay. And what about 5? Where will 5 be inserted? What is the index of 5? 5 mod 7 is
5 only.
5 only. But 5 is already filled. So collision is there. So what happens? It will check for the next position. It is also filled. Now what happens is it will circularly go and check for the next position.
0.
0. So 0 is 3. So 5 will come in location 0. Understood? This is called linear problem. Okay. Now let us see rehashing and then come back to uh, quadratic bobbing. So rehashing means what is like suppose here you can see that um, um, the table is already almost filled, right? Only 2 more elements are free, 2 more spaces are free. So in that case, there is a lot of possibility for collision, right? If it is almost full, then lot of possibility for collision, right? Anyway, data is random, so it has a lot of possibility for collision. So in this case, what you have to do is you have to go for a rehashing. So for rehashing, the first step is to find the new table size. Okay, size of the new table. So how to find the size of new table is just double the current table size. So it's nothing but s into 2. Okay. So for this s into 2, apply the next prime number function. So you're just going to find out the next prime number of s into 2. Understood? You're just doubling the size of the table and then finding the next prime number. So can you tell me what would be the value for this? You will be writing a function for this. Okay, it's not inbuilt. You have to write a function for this. So what would be the value? The current size is 7.
Third, 17.
Yeah, very good. So s into 2 is 14. So next prime to 14 is 17, right? So you have 16. Sorry, 15 is not a prime number. 16 is not a prime number. 17 is a prime number. So 17 is the answer. So now what you will do is you will create one more list with size as 17. Okay. Okay. So now what you do is you just forget about the elements in which order they are coming, because you will not be maintaining these elements. So you have taken these elements and stored it in the table. Okay, so you will not be having these elements. Only these elements will be present inside the table. So take each element wherever there is non-none value. Just take the elements from index 0. Okay, don't change the order from the index 0, and then apply hash function with the new table size, which is 17, right? And then store it in this new table. Fine. So now what is 5 mod 17? 5. So 5 would be, then 10 mod 17, 10.
10.
4 mod 17, 4. 12 mod 17, 12. 80 mod 17,
80.
80. 80 mod 17. 15, right? So 17 5s are 65. So 15 would be the answer. No, not 65. 85. No, I think that would also be 12. Yes, what is 17? 80 mod 17?
12.
12, sure. Okay, fine. So 12, there is a collision. So it will take the next position and then get inserted. Understood? This is rehashing. Again, so when can we do a rehashing is that you can set up a threshold. Like if 70% of the data, if 70% of the table is filled, what you do is you go for rehashing. Again, if this is now after doing a rehashing, you need not maintain this list. You can just delete this memory at all. No need to have this memory. You just remove this from the memory. Use delete function and remove this. Because all these data are being stored in the new table, right? So once this table is full, you create one more table with the next prime of 17 into 2. Understood? Okay. So you can have a threshold, like if 70% of the table is filled, then you can move in for the next new table. Fine. So this is linear problem. So in linear probing, what we did is we took an index where we found using a hash function, we found the index. If there is a collision, we just look immediately for the next location, whether it is free. If not, go to the next location. If not, next go to the next location. Till you find a empty location, you have to keep on searching. Okay. So now, can you tell me why? What is the advantage of doing this type of operation instead of storing it normally 10, 20, 30 like that? Why are we doing why are you performing additional operation and then storing it inside the list? What is the advantage of having this type of an operation or having a hash table? Yes, you can locate element faster, right? See, suppose if it's a normal list, I want to search for 60. Okay, what I would do? I would start from 10 only, right? So 10, 20, not 60, not 60, not 60, not 60. Here we found out 60. Understood? This is the procedure. Linearly, you have to search. Now, what happens in hashing is just apply a hash function. Okay, 60 mod 7, you'll get 4. Directly go to the fourth location. There the element would be found, or it would be found nearer to that. Okay, so within 2 or 3 searches, we'll be able to find out. So, like if the data is not at all present, okay, suppose we have 1 lakh data and then the data is not at all present in that 1 lakh data, what will happen? You have to search for the entire 1 lakh data and then come out to a conclusion that element is not found. Instead, if it is stored in the form of hashing within like So it has to, you will find the index where it has to be stored, and then nearby to that index you will be searching for that element, right? It will be concentrated on a particular set of indices. So searching becomes much faster. Understood? So this is the advantage of hashing. No, so this is linear bobbing. And what is quadratic bobbing is that, so here we moved one at a time, one step at a time. Whereas in quadratic bobbing, what you would do is you will have a square function. Okay, so you will do I into I. So if there is a collision, first you will place it at the corresponding position. So suppose 80, in 80 there was a collision, right? Okay, so you'll try to place it at 12. At 12 you are not able to place. So what you do is you in the next location which you're going to search is, so in normal it was you'll go for 1, 2, 3, 4 like that, right? From the index, suppose from 12 you'll add 1 in linear bobbing. I'm talking about linear bobbing. So in linear bobbing, what will you do? From 12th index you will add 1 and see whether it is free or not. If that is also not free, you will add 2. From 12 you will add 2, then you'll go for 14. If that is also not free, you'll add 3 to 12. Like that you go on, right? Whereas here you just add 1, 4, 6, sorry, 9, 16, like that it goes on. Did you understand what we're doing here? Instead of searching in the next location, we're just squaring and then searching in this particular indices. Okay, so if this is not free, so what you will do is you'll add 1 square to this index. So you'll search at 13. If this is also not free, you'll add 2 square to 12. So you'll go to 16th location. If this is also not free, add 9 to 12th location. So if you put a modulo and then add, you will come somewhere land over here. Are you able to follow? This is quadratic bobbing. Any doubts? Understood the difference between linear bobbing and quadratic bobbing?
Yes, sir.
Okay. Fine. So now, so let us go back to linear bobbing. And then now if you want to delete a particular element, what will you do? If you want to delete a particular element, suppose I want to delete 30. So what will happen if I do a deletion of 30? What's the first step?
Locate the index.
Yeah, first you need to search for the index, right? First you need to find out the position where 30 is inserted. So what is 30 mod 17?
2.
2.
Sorry, 17. Ocha, sorry.
17, 17.
17, sorry. I did.
13, right?
Yes, 13.
Yeah. So it will search at position 13. Position 13, it is checking whether it is 30 or not. It is not 30. So what it will do? It will go to the next position and check whether 30 is present or not. So 30, next position is none, right? It means 30 is not present in the table at all. So we will not search for the entire thing. Okay, it is enough that we concentrate on the index 13.
Sir, but in the data, we can see there is no 30.
Yeah, but logically, how to find whether 30 is present or not? We know as humans, we by seeing itself, we can see that data is not 30 is not present. But we have to write a logic to make the system understand that 30 is not present, right?
Yes.
Okay, so we come to index number 13. We see that 30 is not present at index 13. So go to the next location in linear bobbing. Okay, so here also 30 is not present. So none is there. No more place to search. No need not proceed further. You can stop here itself and then tell that 30 is not present. We can give a warning message. Okay. So now suppose element is present. Suppose I want to delete 80. So do the same process. So first you will apply the hash function for 80. So 80 mod 17, you will get 12. Okay, so at 12th index, 80 is not present. Go to the immediate next location, which is at location 13. We have found 80. So now what you do? We just make this version as none. That's all. Understood? Any doubts? Okay. So now, so we need to understand when to stop searching, right? So in this table, you can see that there is no none at all, right? So if I keep searching for none, to suppose I want to search for 55 in this table. Okay, now what happens if I search for 55? Index to be searched would be 5. So at 5, 55 is not present. So I'll go to the next position. Here also not present. Here also not present. Here also not present. So it keeps on searching till none is there. So till here it came, it's not present. Again, next position is also not none. So if you don't write the logic properly, what happens is it will continue infinitely. It will keep on searching. So what could be the second stopping position, stopping condition? Yes. So second stopping condition, one is if none is reached, we have to stop. Second stopping condition is if we come back to the same index again. So we started from 5. If we come back to the same index again, then also you have to stop searching. And you can print that element is not found. Okay. So keep everything in mind. So you are going to implement the logic. Okay, you have the template in the ebox. You're just going to fill the codes. Okay. For every template, you will be writing the codes. And keep all these things in mind. So while searching, you should search till none is present. And if there is no none is present at all, you should stop when the same index has reached. So all those things you keep in mind. Okay. Fine. So this is about linear bobbing and quadratic bobbing. Now coming to the third algorithm, which is separate chaining. So in these two algorithms, what we did is we had the data within the table itself, right? So the table, see, like while the start of the data structures class itself, I told that all the data structures can be implemented using list and linked list, right? So this is like a list implementation. So within the list, you are storing the data. So separate chaining is nothing but it is a linked list implementation of hash table. Okay, so it is very simple. What you do is like okay, let us take this data. And the table size is again 7. Okay. Now these are not going to be the datas. These are going to be linked list head values. Understood? These are all going to be the linked list head values. Now the hash function is not going to change. It's the same hash function. So modulo 7. Sorry. So what is 12 modulo 7? 5. So now what happens is instead of storing 12 inside this like inside this table, you will just create a new node for 12 and then just store the address of 12 over here. So address of 12 is what? Let us take the Excel address itself. It is AB312. Okay. So I'm just writing the column value, row value. That's it. So AB, so column value, row value is 312. So I could have used the same denotation in graph also, right? Okay, fine. So like AB 312 and then 12 you have inserted. Now next is 4. So 4 will get inserted over here. So 4, here it is AB 311. Okay, and then 10. Where will 10 be inserted? Third index. Okay. AB 310. Then 80, 5,
Oh, sorry, 7.
right? 5 only, no?
3.
3, sorry. So now what happens? So 80, 77, so 3, yeah. So 3 in third index. Now what you do is you just add it as the next element. We just append it to this linked list. That's all. So this is called separate chaining. So now 5, where will 5 be inserted? It will be appended to the list 5. So now what you do is instead of adding 5 next locations, you just append it to the particular linked list. That's all. Understood? Any doubts in this? Now if you want to search for a particular element, you need not search for the entire thing, right? Just if you want to search for 80, just in this list you search. Okay, so 80 mod 7 is 3. So only in the third list 80 is going to be present. Nowhere else it is going to be present. Okay, my search gets concentrated only in this particular list. Are you able to get it? That's it. This is your separate chaining algorithm. Okay.
Yes, sir.
Now let us see the different terms. Okay, now you tell me which algorithm falls under which term. Okay, so one is open hashing or closed hashing or open indexing or addressing. So open hashing. So what I mean by open hashing is that you are not limiting the elements to be present only inside the hash table. You are letting the elements go out of the hash table also. For example, here. So these elements are not present inside the hash table at all. They are outside in a form of a list. So this is called open hashing. So the same name, the other name for, not same name, the other name for open hashing is closed indexing. Closed indexing means what? So if you take 10, 10's index is 3, 3 is not going to be present at any other index at all. It is going to be present only at third index. That is called closed indexing. Okay, so now let us see for closed hashing. Closed hashing means you're not going to let the elements out of the hash table like this, linear bobbing. All the elements are present inside the hash table. And then open indexing means like the element need not be present at which index it is meant to be. Right? For example, here 80 is meant to be present at index 3. Right? So whereas it's not located at 3, it is going to location 6. Understood? So it is open indexing. Open indexing. Are you able to follow?
Yes, sir.
Yeah. That's it. So understood hashing. So this is how hashing happens. So every like small steps can be written as functions. Okay, for next prime you can write a function. Okay, for If there's a collision, you can go for you can call a function to like do a probing or do a separate chaining. Okay, so just go through the problems in eBox. So if you have doubts, we can discuss in the next class. So there will be only 3 problems in this hashing topic. So linear probing, quadratic probing, and open hashing. I mean separate chaining. Okay, fine. So shall we wind up? Yeah. So thank you all. We can meet in the next class, day after tomorrow.